So in this video, we're going to be talking about sequences and how to find the recursive or the explicit rule for different sequences and how to derive the following numbers given a sequence. So what is a sequence? Well, a sequence is just a group of numbers that can be finite or infinite. You know that it's finite whenever it stops. So this is a sequence of 4 numbers, 1, 2, 3, and 4. And we can know that it's infinite if it looks something like this. Note that even though it has dots, it could also be finite if we're given an end value. So in this case, that's a bad example. So in this case, this would be a finite sequence as well, because we know that these dots are just representing 5 and 6. Right? So just because they're dots, that doesn't mean it's it's infinite. The main two things with sequences is identifying the pattern and then writing it out using math terms. So we usually refer to a sequence as A, and then each element in the sequence as the nth term. So this would be the first term, the second term, third term, fourth term, and that's just their position, not their actual value. So for example, I can write a whole new sequence. I'm going to write this as 2, 4, 6, 8, and so on. And if you were looking for the second term of this, it would be 4, right? Because 1, 2, 3, 4, and so on, right? So how do we actually write that out? Well, it'll be in a sub n. This is the notation that we would use. So if I want the value of 6, I know that 6 is the third term. So A of position 3, so where n is equal to 3, will equal 6, right? But how do I find out A sub 5? Well, I know I have 1, 2, 3, 4, but what is my fifth term? Well, we can get into the two types of rules to find out the next term. The recursive rule and the explicit rule. So starting off with our recursive rule, how do we get to the next element using the ones that we all already know? So if I draw out a little table for this, I'm going to draw a table. On this side it's going to be n, on this side it's going to be a sub n. So this is the position and this is the value. The position, we're going to do 1, 2, 3, 4. These are the ones that we know. And the values for each are going to be 2, 4, 6, and 8. All right, and these two go on infinitely. If I want to find the value at position 5, I have to look at what has been happening in the past. So this would be 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. So we know the next term, if we add 2, is going to be 10. Right? So how do we write that out? Well, let's first write it out in words. The nth term, right, is the same as the previous term plus 2. And to write that, we can say a sub n, which is our current term. That kind of looks like n. A sub n, or our nth term, is going to be our previous term plus 2. Now, how do we write out our previous term? Well, we know that n is just some integer value. So if we look at 4, 4 would be a sub 2, 2 would be a sub 1. And we know that 1 is just 2 minus 1. So this will be the same as a 2 minus 1. In the same sense, we can say that the previous term is always a n minus 1. So our recursive equation here would be a sub n equals a n minus 1 plus 2, or the element that we are finding is equal to its previous element plus 2. But that's not all. You see that there are some bounds of what we can plug into n. We can't plug in -1 into n because that doesn't make sense. So there are two rules. One, n has to be an integer, right? Because it's a position. And we also know in this case that n has to be greater than or equal to 2. Why 2? Well, if we plug in 1, we don't have a 0th position. 1 minus 1 is 0. So, as well as having a rule, we also must have a starting point for our recursive equation. So, in this case, we'll have a1 equals 2. So you must write these 4 different parts in order to write a recursive equation, right? N is an integer, n is greater than or equal than 2, a of 1 is 2, and a of n equals a of n minus 1 plus 2. Now let's write our explicit equation. So for our explicit equation, we have to write a of n in terms of just n. We cannot have a previous term. Why is this helpful? Well, what if I ask you, using our previous equation, and I'll just keep this up here for simplicity. Let me ask you, what is the 100th term? Well, you would say that the 100th term is the 99th term plus 2. Now I find the 99th term. And the 99th term is the 98th term plus 2, and so on. But that's too time consuming. How do we find a rule that we can immediately plug in n and get us an output? Well, in this case, we can go back to our table, right? So I'm going to draw out my table again, and a of n. N is 1, 2, 3, 4. We know that a of n is 1, but this time I'm going to really think about what I'm really doing. So my next value, instead of saying this is 4, I'm going to say this is 2 plus 2. My next value is 2 plus 2 plus 2, and so on. We see a pattern starting to come here. We can rewrite all of these as 2, 2 times 2, 2 times 3, 2 times 4. This is just 2 times 1. So we know that a of n equals 2 times whatever our n is. A of n equals 2n. So we've identified some sort of parallel between our n and something we plug in for our expression. So in this case, you would just plug in your n times 2 to get us your answer. So now, if we were to go back and try to find a of 100, we know that a of 100 equals 2 times 100, same as 200. One more thing, looking back at our explicit rule, we have to also identify some bounds. We know in this case that whenever we plug in our n has to be an integer, but we don't have to identify an initial value. We do not have to do that. Instead, we can write n is greater than or equal to 1. We couldn't do greater than or equal to 1 last time because 1 minus 1 is 0, and we didn't have a 0th value. But in this case, if you plug in 1, everything works. So this is all we need, this and this. Let's see if we can write an explicit rule for this set of numbers. Well, let's first draw our table. N and a of n. 1, 2, 3, 4, 5, 0, 3, 8, 15, 24. Let's try to write these in relation to each other. So this will be 0 plus 3, 3 plus 5, 5 plus 10, 10 plus 14. Looking at these numbers here, these numbers that we're adding don't seem to have any connection to these numbers here. Maybe plus 1, plus 2, plus 6, plus 9. It doesn't seem like too much of a pattern here. So maybe it's not plus. We can look at times, but nothing times 0 will get us 3. So it's not that. Well, let's see what the individual numbers are made out of. Well, we know that 24 is 4 times 6, and 15 is 3 times 5. 8 is 2 times 4, and from there you start to see a pattern. Well, 4, 3, 2, 1 times 3. It seems like you have to multiply the two closest integers to n to get us a of n. So this will be 0 times 2. So in this case, our a of n will equal, well, to get our first number, we have to do n minus 1. To get our second number, it will be n plus 1. Now, the main thing you have to recognize here is that we went through multiple different efforts to try to identify the pattern here. Sometimes the pattern will be based on the previous numbers, while other times it will be based on the numbers itself. In this case, we identified no pattern between the numbers, so we have to look at the composition of the numbers itself. So make sure you are looking out for these types of patterns. In this case, this is our explicit rule. And since there aren't any connections between these numbers here, there most likely will not be a clear-cut recursive pattern. So this is our explicit rule. Note again that n is an integer, and this is possible for all values greater than or equal to 1. Now, as a thought experiment, let's say I got rid of this part and we stopped it here. We can identify this as a finite sequence, right? But n cannot be greater than 1, 2, 3, 4, 5 because there doesn't exist anything past our fifth term. So in that case, you will have to add an extra boundary here to know that 5 is greater than or equal to n, which is greater than or equal to 1. Make sure you're always looking out for infinite versus finite sequences. Now let's say I have a series 0, 1, 1, 2, 3, 5, 8, and so on. We can first identify this as an infinite series, so we don't have to worry about an upper bound. Now whenever we draw out our table, we have to identify whether the relationship is with the numbers itself, or how the number is composed, or between the numbers. So I'm just going to write out the first, let's say, 6 terms. 1, 2, 3, 4, 5, 6. And this will be 0, 1, 1, 2, 3, 5. Now, what are the patterns? Well, we know that multiplication won't work, but let's try it. Let's say we multiply this by what? Well, we can't really multiply to get to 1. So that's why multiplication won't work here. You might have looked at this and said, well, we're multiplying by 1, then we can multiply by 2, but make sure your rule works for every single number in the sequence, because 2 times 3 does not equal 3. So we know it's not multiplication. Let's try adding something. So from 0, you have to add 1. From 1, you add 0. From 1 to 2, you add 1. Here, you add 1. What's going on here? Well, we can identify no solidified pattern here. Or can we? We can see here that whenever we add 1 and 1, we get 2. And what are the two previous terms behind 2? 1 and 1. Same could be said for 2 to 3. 2 plus 1 is 3. And what are the two prior terms? 2 and 1. This is a hard pattern to find, but it's a cool one. So you know that the previous two terms always add together to give you the next term. 1 plus 1 gives you 2. 2 plus 1 gives you 3. 2 plus 3 gives you 5, and so on. So now we can write a recursive equation for this. A term 2 before our current one would be a n minus 2. and 1 before would be a n minus 1. So our pattern would be a of n equals a n minus 2 plus a n minus 1. Now we have to set up some bounds. So we know that n is an integer, and we know that n has to be greater than or equal to what? Well, we have to identify that if we set this to 0, it'll give us -2 and -1. That doesn't work. If we set it to 1, it'll give us 0 and -1. We usually would set this to 2, but even though this gives us 1, this would give us 0. And we don't want a 0 in our sub because we don't have a 0th term. Therefore, n has to be greater than or equal to 3. Also, because this is recursive, we have to identify the previous values as a starting point. So in this case, you can say a of 1 is 0 and a of 2 is 1. These are the components you would need for a proper answer. A of n equals a of n minus 2 plus a of n minus 1, which is just the current term equals the sum of the two prior terms. N has to be greater than or equal to 3, because if we're looking at this term, you can't add 0 and a non-existent term. So you have to start at the third term. And we have to identify our starting two terms. Because if we don't, then once again, you have a problem with non-existent terms. Now the best way we can think about this is to separate this into a top pattern and a bottom pattern. So let's first look at the numbers on top. The numbers on top are 1, 3, 9, 27, 81, and so on, right? So what is happening between these terms? Well, I can identify this clearly as we're going to multiply by 3. So how do I write that explicitly? Well, I'm just going to call this, I don't know, we'll call this b. All right, we're going to split our numerator and our denominator. We'll have this at c, 1, 1, 2, 6, 24, ... All right, so for our b, we know that every term of b is 3 times what? Well, the value here is 1. The index here is 1, index here is 2, index here is 3, and so on. So we can't do 3 to the nth power, because 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. What we notice here is that it's staggered, so that the 1, 3 to the first, corresponds to 3, but it should correspond to 1. In this case, in order to push it back, we have to push it back by how much? 1. So instead of 3 to the n, we're going to do 3 to the n minus 1. In this case, if we plug in 1, we get 3 to the 0th, which is 1. If we plug in 2, this will be plug in 1, 3 to the 0th equals 1. If you plug in 2, 3 squared is 3, 2 minus 1, which is 3 to the first, is 3. All right? So we have to identify that although we're multiplying by 3 each time, we have to know what our starting point is. And that whenever we plug in 1, you have to subtract it by 1 to get 3 to the 0th equals 1. So we've identified our top pattern. All right? Now for our bottom pattern, we see this sort of random arrangement of numbers here. So let's try to make some sense of this. Now I can't really see a concrete pattern here, as I can see here with a times 3. So I'm going to write out a chart. N, and this will be C of n, right? Because this is our C table. I have 1, 2, 3, 4, 5, 1, 1, 2, 6, 24. Here we come to a sequence of numbers, which is a commonly seen pattern that uses factorials. What does that mean? Well, a factorial, if I take n to the factorial, but this is the factorial symbol, that is n times n minus 1 times n minus 2, all the way until you hit 1. So whenever I'm looking at this pattern, this 1, 2, 6, 24, this commonly known pattern, I know this is 1 factorial, 2 factorial, 3 factorial, and 4 factorial. But what does this mean? Well, this means that this is just 1, this is 2 times 1, this is 3 times 2 times 1, and this is 4 times 3 times 2 times 1. This is a very important number series to know. Now, one thing, if this sequence was instead 0, 1, 5, 23, make sure you identify that this is just n factorial minus 1. All right? So don't be caught off guard whenever you see numbers that are close to patterns that you may recognize but are slightly off, because you may be able to change it just a little bit. But oh wait, it can't be n factorial. Why? Because 2 factorial is 2. Once again, they're staggered. If we look at the positions, 1, 2, 3, 4, 5, the positions are staggered the wrong way. They should be pointing like this, but instead they're pointing 1 and 4. So instead of n factorial, let's try to get 1 below. So we know that 1 is 1 factorial, so we subtract 1 from 2 to get 1 factorial. 2 is 2 factorial, and we can get 2 by doing 3 minus 1. 6 is 3 factorial, and we can get 3 by doing 4 minus 1. So our pattern here is n minus 1 factorial. Oh wait, you say, we have a problem. 1 minus 1 gives us 0. But what is 0 factorial? Well, in this case, it's good to know that 0 factorial is just the same as 1. So our rule works here. So what do we know? We know that our pattern for our denominator is that c of n equals n minus 1 factorial. Now we can tie this all together. So we've identified our two rules. We have our top, or our numerators, are 3 to the power of n minus 1, and our denominators is n minus 1 factorial. So now we can write our explicit rule just like this. A of n equals 3 to the n minus 1 over n minus 1 factorial. We're just combining our sequence we found for our numerator in our denominator. We know that n is an integer, and the values that we can plug in, we know that n has to be greater than or equal to 1. Once again, anything raised to the 0th power, if we plug in 1, 1 minus 1 is 0. Anything raised to the 0th power is 1. And 0 factorial is 1 as well. So this works. This is our answer here. All right, let's say we have this sequence. Once again, we're going to split it up into top and bottom. So we're going to have b of n, or in this case will just be b, will equal 2, 6, 24, 120, 720. And we'll have our c be 1, 3, 7, 15. And this should be 31. So what is the sequence that we can identify on top here? Well, look at these numbers. We've already identified these numbers as being factorial numbers. So b of n equals n factorial. Done. But wait, we know that 1 factorial is 1 and 2 factorial is 2 and so on. But if we plug in 1, we'll get 1. If we plug in 1 for n here, b of 1, we'll get 1. But b of 1 is 2. Well, we identify that this sequence is once again staggered. So in this case, it won't be n factorial, but we have to add 1 to n before we take the factorial, because we know that this is the same as 2 factorial. 3 factorial, 4 factorial, and so on. So our value n, you have to add it by 1 before you factorial it. All right. So if I plug in 1 now, okay, 1 plus 1 is 2, 2 factorial is 2. If I plug in, let's say 3, position 1, 2, 3, 3 plus 1 is 4, 4 factorial is 24. All right, so we've identified our top pattern. What's our bottom pattern here? Well, it doesn't seem like any adding pattern. So this is a plus 2, then plus 4, then plus 8, then plus 16. Oh wait, it is an adding pattern. So now we have to identify a pattern on top. I mean on the bottom. So we're going to write out our table here because I don't see any clear-cut pattern here. 1, 2, 3, 4, 5, and 1, 3, 7, 15, 31. Let's do some addition. Plus 2, plus 4, plus 8, plus 16. I thought this would be adding just by 2 each time, but it's not. In this case, how can we rewrite these terms? Well, this adding 2 could be just the same as adding 2 to the power of 1. Adding 4 could be the same as adding 2 could be the same as adding 2 to the power of 1. Adding 4 could be the same as 2 to the power of 2. And we have a pattern here. We know that these are all factors of 2. But writing them out better, we know that 2, if you add by 2, you're just adding by 2 to the first. If you add by 4, you're adding by 2 to the second. By 8, you're adding 2 to the third, and so on. So how do we write that? Well, in this case, you have to use the previous number in order to determine the current number. But we don't want that. We want an explicit rule. So how do we better represent these? Well, what's interesting is that we've identified this pattern 2, 4, 8, 16, and we know that these are all factors of 2, or rather 2 raised to some integer exponent. But notice these numbers in relation to the sequence we already have. Isn't 1 just 1 off 2? 3 is just 1 less than 4. 7 is just 1 less than 8, and so on. From here, we can identify a better pattern instead of using recursion. From here, we know that 3 is the same as 2 squared minus 1. 7 is the same as 2 cubed minus 1. 1 is the same as 2 to the first minus 1. And here we have a real pattern. 2 to the fourth minus 1, and 31 will be 2 to the fifth minus 1. So if we rewrite all these numbers as their equivalent, we can see how we can add an n to all of these. So 1 is 2 to the first minus 1, 2 is 2 to the second minus 1, 2 to the third minus 1. This is 2 to the fourth minus 1, this is 2 to the fifth minus 1. And we can identify that the number changing here, which is just the exponent, 1, 2, 3, 4, 5, is the same as the number that changes here. So in this case, we know that C, right over here, C of n equals 2 to the power of n minus 1. Now we have our top and our bottom pattern. We know that A sub n equals n plus 1 factorial over 2 to the n minus 1. N is an int. And we know that n has to be greater than or equal to 1. In this case, we're defining it explicitly, so it's not greater than or equal to 2, it's just greater than or equal to 1. Notice that this sequence right here is not infinite, meaning we have to set a top bound of 1, 2, 3, 4, 5. So this will be our final answer here. Now, let's say we have a sequence that has a positive, then negative, then positive, then negative values. So we have the signage changing on each term. So the first step is to just consider the pattern with all positive signs to only identify what's changing on the bottom. Well, if we look at the bottom is going 2, 4, 8, 16, and so on, which we know are just powers of 2. 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and so on. So we know that our pattern on the bottom is going to be 2 to the power of n, right? And that will get us a full positive set. But it has to be positive the negative and positive the negative. Now, how do we change whether it's positive or negative without changing the actual value of this? Well, we can multiply by -1. So in this case, we have our actual value, and to check its signage, we can just multiply it by -1. But this makes a problem. Now, this will always be negative. So how do we make sure it's only negative on every other term? So what we can observe here is that it's only negative on the even terms, and it's positive on the odd terms. So how do we change whether this negative is positive or negative? Well, we can raise it to an exponent. So in this case, if we raise -1 to 1, it'll bring us -1. -1 to 2, it'll bring us +1. -1 to 3, it'll bring us -1. So we see whenever we raise it to an odd power, it gets us negative, and an even power will get us to a positive. But that's the opposite of what we want. So how do we change it? Well, we know that an even number is always 1 off of an odd number. So even -1 is an odd number, right? Or you can do even +1 is an odd number, whichever way works. So in this case, we can raise it not to just n, but n plus 1. What this does is that, let's say we have our first term. If we plug in 1, into here, then n plus 1, 1 plus 1 will give us 2, so it'll be positive. Whenever we plug in an even number into n plus 1, that'll get us an odd number. Whenever we plug in an odd number, it'll get us an even number. 3 plus 1 will give us 4, while 2 plus 1 will give us 3. From here, we can change the signs. So what did we do here? We had to do two things. One, we had to separate it between its values and whether it's positive or negative. Two, we have to identify how the values change. In this case, we saw that the denominators are just powers of 2, and we could just use that as our rule. And 3, we have to bring in the changing positive and negative numbers in a way that works for every single case. In this case, multiplying by -1, all of it to the n plus 1 power, because we start off on a positive. Of course, in this case, n will be greater than or equal to 1, and n is an int. How do we start here? Well, we can't identify an adding or multiplying pattern here because we want to find an explicit rule. So what we can do is that we can use all that we know so far to rewrite these numbers in a way that we can find a pattern. In this case, I can see that if I write out my table, 1, 2, 3, 4, and so on, instead of writing this out as 1, I can write this out as 2 minus 1. Why is that important? Well, because I can write the 3 as 2 plus 1. Then 2 minus 1, 2 plus 1. We know for our first term, this 1 has to be negative, and for a second term, the 1 has to be positive. So if we're starting off as a negative, we know that -1 to the nth will give us a negative on our first term and positive on our second term, and so on and so forth. Then we can just add that to this 2, or let me just write it like this to make it make sense here, which will give us the pattern that we need. In this case, if we plug in, let's say 4, -1 to the fourth is 1, which will give us 3. If I plug in 5, Negative 1 to the fifth is negative 1, which would be 2 plus minus 1, the same as 2 minus 1, which is 1. This is a very interesting problem to tackle, but at the end, using our rules with sign flipping and identifying common characteristics of our values, we can really figure out how to solve this problem. Now let's just write out the rule. The rule in this case, the nth term will be our 2 plus negative 1 to the nth power, where n is greater than or equal to 1, and n is n int. Thank you so much for watching, and I hope this helped you identify recursive versus explicit rules and how to properly notate them and figure them out from a sequence.